October 13, 1943. Professor Hidetoshi Nakamura carefully removed the thick canvas cover from the captured American radio equipment in the basement laboratory of the Tokyo Imperial University Engineering Department. The fluorescent lights hummed overhead as 5 of Japan's most accomplished radio engineers gathered around the olive-drab metal case that bore the marking SCR-300 radio set. For 18 months, Japanese military intelligence had insisted that American portable radio equipment was crude, unreliable, and severely limited in range. Reports from the front lines consistently described American infantry units that could somehow coordinate attacks across impossible distances, calling in artillery fire and air support with precision that suggested far more sophisticated communications than Japanese doctrine allowed for. The official assessment remained unchanged. American soldiers relied on primitive equipment operated by poorly trained conscripts from a nation that prioritized quantity over quality. Yet the evidence arriving from Guadalcanal, New Guinea, and the Marshall Islands told a different story. American forces maintained constant communication across terrain, where Japanese units lost contact within hundreds of yards. Their infantry coordinated with artillery, naval gunfire, and close air support with a reliability that defied explanation. The SCR-300 radio set captured intact from a fallen American paratrooper near Bougainville was about to reveal why. What Nakamura and his team discovered over the next 72 hours would fundamentally alter Japanese understanding of American industrial capabilities, technological sophistication, and the mathematical realities of radio wave propagation. The weight of American manufacturing supremacy was about to be measured not in tons of steel or gallons of fuel, but in the precise engineering of vacuum tubes, the quality control of mass-produced components, and the revolutionary concept of standardized battlefield communications equipment designed for ordinary soldiers. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The systematic examination of the SCR-300 would expose an industrial philosophy so fundamentally different from Japanese military thinking that it challenged every assumption about how modern warfare should be conducted. Where Japanese radio equipment required skilled technicians and careful handling, American equipment was designed for abuse by infantry soldiers in jungle conditions. Where Japanese doctrine emphasized preserving expensive equipment, American design assumed radios would be lost, damaged, or destroyed, and had planned accordingly. The examination began on October 13, 1943, in the secure basement of Tokyo Imperial University's engineering building. Professor Nakamura, former chief engineer at Nippon Electric Company and designer of several Japanese military radio systems, led the investigation. With him were specialists in vacuum tube technology, antenna design, frequency control systems, and battlefield communications doctrine. They approached the American equipment with the methodical precision that had made Japanese engineering renowned throughout Asia. The SCR-300 was immediately recognizable as something entirely different from any military radio they had encountered. Weighing 35 pounds, complete with batteries, the entire system was designed to be carried and operated by a single soldier. Japanese equivalent equipment required a team of 3 men and could only be moved by vehicle or pack animal. Yet, initial examination suggested the American radio might actually be more sophisticated than Japan's fixed station equipment. The outer case was constructed of heavy aluminum alloy, with reinforced corners and waterproof seals, protecting every connector and control. Captain Satoshi Hayashi, a communications officer who had served in the Philippines and witnessed American equipment in combat, noted that the construction quality exceeded anything in the Japanese inventory. The radio was designed to withstand tropical conditions, repeated drops, water immersion, and the general abuse that infantry equipment endured in combat. Opening the case revealed the first shock. Inside, 18 vacuum tubes were mounted in shock-absorbing sockets, with spring-loaded retainers that protected the fragile glass envelopes from impact damage. Each tube was individually secured, easily replaceable, and marked with clear part numbers and specifications. The entire radio frequency section was built around a super-heterodyne receiver design that Japanese engineers recognized as theoretically superior but prohibitively expensive for field equipment. Dr. Kenji Yamamoto, Japan's leading expert on vacuum tube technology, carefully removed one of the tubes for detailed examination. The glass envelope was perfectly clear, the filament precisely aligned, and the internal electrode structure manufactured to tolerances that would have required weeks of skilled labor in Japanese factories. This was a 6AK6 remote cutoff pentode, a tube type that Japanese industry had never successfully mass-produced due to the precision required in electrode placement and the complexity of the manufacturing process. Yet the Americans had installed 18 of these precision tubes in a radio designed to be carried by infantry soldiers and operated under battlefield conditions. The part numbers on each tube indicated standardized manufacturing specifications, interchangeable components, and quality control systems that could produce thousands of identical units. Yamamoto noted in his preliminary report that the single tube he examined represented more precision manufacturing than most complete Japanese radio sets. The frequency control system revealed even more disturbing implications. The SCR-300 operated on frequency modulation across 40 preset channels in the VHF band between 27 and 39 megacycles. Each channel was crystal-controlled for precise frequency stability, but unlike Japanese crystal-controlled equipment that required careful tuning and adjustment, the American radio automatically switched between preset frequencies at the turn of a selector knob. Lieutenant Takeshi Morimoto, a signals intelligence specialist who had intercepted American communications throughout the Pacific Campaign, examined the antenna system with growing amazement. The SCR-300 used a telescoping whip antenna that extended to nearly 8 feet in length but collapsed to less than 2 feet for transport. The antenna was connected through an impedance matching network that automatically optimized signal transfer, regardless of frequency selection or antenna position. Japanese portable radios used fixed-length antennas that required manual adjustment for each frequency and careful positioning for optimal performance. The American system was designed for soldiers who had no technical training and needed communications equipment that worked reliably regardless of how it was handled. The engineering philosophy behind every component was becoming clear. Designed for operation by ordinary soldiers under combat conditions rather than by trained technicians in controlled environments. Over the next 3 days, the team conducted exhaustive tests of every function and capability of the captured radio. They connected the SCR-300 to laboratory power supplies, precision test equipment, and antenna systems that filled the underground facility. Each test revealed capabilities that challenged fundamental assumptions about battlefield communications and the industrial capacity required to produce such equipment in quantity. The transmitter section produced 18 watts of clean frequency modulated signal with automatic level control that maintained constant output power regardless of battery voltage or component aging. The modulation system used a reactance tube modulator that provided distortion-free voice transmission superior to any Japanese military equipment. Most significantly, the entire transmitter was designed for immediate operation without warm-up delay, technical adjustment, or operator skill beyond pressing a transmission button. Range testing revealed the most shocking discovery. Connected to a properly erected antenna system, the SCR-300 maintained clear, static-free communication over distances exceeding 20 miles under favorable propagation conditions. Under typical battlefield conditions with portable antennas, reliable communication range extended to 8 miles, more than 4 times the range of comparable Japanese equipment. The mathematics of radio propagation meant that this range advantage translated into coverage areas 16 times larger than Japanese forces could achieve. An American infantry unit with SCR-300 equipment could coordinate operations across an area of over 200 square miles, while Japanese units were limited to coordination areas of approximately 12 square miles. Dr. Nakamura began preparing his preliminary report to Imperial General Headquarters, knowing that each sentence would contradict official assessments and intelligence estimates that had guided Japanese military planning for over 2 years. He wrote that the SCR-300 represented not just superior American technology, but an entirely different approach to military communications and industrial organization. The captured radio was not an experimental prototype or specialized equipment issued to elite units. Every aspect of its design indicated mass production for standard infantry use. The Americans were apparently equipping ordinary soldiers with communications equipment more sophisticated than Japan's highest command-level radio systems. The implications for battlefield coordination, tactical flexibility, and overall military effectiveness were staggering. Testing continued around the clock as the team explored every circuit, measured every component, and documented every specification. The battery system used standardized BA-70 dry cells that provided 12 hours of continuous operation or 72 hours of intermittent use. The batteries were commercially manufactured units identical to those used in civilian applications, but connected through a power management system that maximized operating life and provided accurate charge level indication. Japanese military radio equipment used specialized batteries that were expensive, difficult to manufacture, and often unavailable in forward areas. American equipment was designed around readily available commercial components that could be manufactured by existing industrial facilities and distributed through standard military supply channels. Even the battery design reflected the fundamental American philosophy: use industrial capacity to solve military problems through mass production of standardized components. The receiver section of the SCR-300 incorporated automatic volume control, noise-limiting circuits, and frequency drift compensation that provided clear reception under conditions that would render Japanese equipment unusable. The super-heterodyne design used dual conversion to eliminate interference and provide exceptional selectivity. Most remarkably, the entire receiver was designed for single-knob tuning operation that required no technical knowledge or training. Captain Hayashi, who had monitored American communications during combat operations in the Philippines, confirmed that ordinary American soldiers operated these radios with confidence and effectiveness that contradicted everything Japanese intelligence had reported about American technical training. The equipment was apparently designed to be foolproof, allowing effective use by soldiers whose only training presses was basic voice procedure and frequency selection. The antenna matching system revealed sophisticated engineering that automatically compensated for variations in antenna length, ground conditions, and environmental factors that would require constant adjustment with Japanese equipment. The SCR-300 maintained optimal performance regardless of how the antenna was positioned, what terrain it operated over, or what atmospheric conditions affected propagation. Professor Nakamura's detailed technical analysis filled over 60 pages of measurements, circuit diagrams, and component specifications. His conclusions, however, could be summarized in a few devastating sentences. American industry had successfully mass-produced battlefield communications equipment that exceeded Japanese laboratory prototypes in sophistication, reliability, and performance, while remaining simple enough for operation by untrained personnel. The manufacturing precision evident in every component indicated quality control systems and production capabilities that Japan simply could not match. More disturbing still, the standardized design and commercial component usage suggested that America was producing these radios in quantities that would equip their entire military force with communications capabilities superior to Japanese command-level equipment. By October 16th, the examination was complete. The SCR-300 had been thoroughly tested, completely documented, and partially disassembled for component analysis. Every vacuum tube had been characterized, every circuit traced, and every specification measured. The results painted a picture of American industrial capability that fundamentally challenged Japanese strategic planning and military doctrine. The radio operated across 40 crystal-controlled channels with the precision and reliability of fixed-station equipment, yet could be carried and operated by a single soldier. The frequency modulation provided static-free communication, immune to atmospheric interference that degraded Japanese amplitude modulation systems. The automatic circuits eliminated the need for technical operators and allowed effective use by ordinary infantry. Most significantly, the 20-mile communication range meant that American forces could coordinate operations across areas 4 times larger than Japanese doctrine considered possible for portable equipment. A single American infantry regiment with SCR-300 radios could maintain communication across a front that would require division-level communications for Japanese forces. The tactical implications were overwhelming. Dr. Yamamoto submitted a separate report focusing on the manufacturing aspects of the captured equipment. His analysis of the vacuum tubes, circuit boards, and mechanical components revealed production techniques and quality control systems that represented a fundamental advancement in military manufacturing. Every component was manufactured to commercial precision standards yet designed for military durability requirements. The vacuum tubes showed no hand adjustment marks, no individual calibration, and no variations that would indicate skilled assembly. These were precision components manufactured by automated processes and quality control systems that produced thousands of identical units. Japanese vacuum tube production required skilled technicians for assembly and individual testing for quality assurance. American industry had apparently solved the fundamental problem of producing precision electronic components using mass production techniques. The same industrial philosophy that manufactured automobiles and household appliances had been successfully applied to military radio equipment. The result was battlefield communications equipment that combined laboratory precision with assembly line production efficiency. The implications extended far beyond radio communications. If America could mass-produce precision electronics for military use, they possessed manufacturing capabilities that could be applied to any technological requirement. The industrial capacity evident in the SCR-300 suggested that American military equipment superiority was not limited to specific items, but represented a systematic advantage across all categories of military technology. Lieutenant Morimoto's intelligence assessment focused on the operational implications of American communications superiority. His analysis of intercepted American radio traffic during recent Pacific campaigns confirmed that ordinary American units routinely coordinated operations across distances that Japanese forces could not achieve with their best equipment. American infantry companies maintained constant communication with battalion headquarters, artillery units, air support, and naval gunfire platforms simultaneously. This coordination capability allowed tactical flexibility and responsiveness that Japanese forces could not match. American units could rapidly concentrate firepower, coordinate complex maneuvers, and adapt to changing battlefield conditions with effectiveness that reflected superior communications as much as superior training. The frequency modulation used by American equipment provided security advantages that compounded their tactical superiority. Japanese monitoring equipment designed for amplitude modulation could not effectively intercept FM transmissions, creating a communications environment where American forces could coordinate freely, while Japanese forces operated with limited intelligence about enemy intentions and movements. By October 20th, all preliminary reports had been submitted to Imperial General Headquarters through appropriate classified channels. The conclusions were uniform across all technical, manufacturing, and intelligence assessments. American military communications equipment represented technological and industrial capabilities that Japan could not match with existing resources and manufacturing capacity. Professor Nakamura received orders to continue detailed analysis and prepare comprehensive technical intelligence reports for distribution to Japanese military research facilities. His team began the painstaking process of reverse engineering every circuit, documenting every manufacturing technique, and developing recommendations for Japanese military communications development. The work would continue for 8 months, producing over 400 pages of technical documentation, circuit analysis, and strategic assessment. Every page confirmed the initial conclusions reached during the first 72 hours of examination. America possessed not just superior communications equipment, but superior industrial capability, superior design philosophy, and superior integration of technology with military doctrine. The detailed circuit analysis revealed engineering decisions that reflected fundamentally different approaches to military equipment design. Where Japanese radio engineers optimized for material conservation and component efficiency, American engineers had optimized for reliability, ease of manufacture, and operational simplicity. The SCR-300's power supply circuit used components rated for operating conditions far exceeding normal requirements, ensuring reliable operation under extreme battlefield conditions. Dr. Yamamoto's analysis of the power management system revealed sophisticated voltage regulation circuits that maintained stable operation despite battery voltage variations, temperature extremes, and component aging effects that would render Japanese equipment inoperative. The American design included redundant protection circuits, automatic shutdown systems, and failure indicators that allowed field diagnosis without technical expertise. The frequency synthesis section incorporated automatic frequency control circuits that Japanese engineers had considered theoretically interesting but practically impossible to implement in portable equipment due to cost and complexity constraints. The American implementation used precision components manufactured to tolerances that required specialized production equipment and quality control systems that simply did not exist in Japanese industry. Professor Nakamura's team conducted exhaustive environmental testing using equipment borrowed from Japanese aircraft manufacturers. The SCR-300 continued operating reliably at temperatures ranging from -40 degrees Fahrenheit to +160 degrees Fahrenheit, humidity levels up to 95%, and vibration frequencies that would destroy most Japanese military equipment within minutes of exposure. The mechanical design revealed engineering sophistication that extended beyond electronic components to encompass industrial design principles that Japanese manufacturers had never successfully implemented. Every control knob, switch, and connector was designed for operation by soldiers wearing gloves, in darkness, and under combat stress. The human factors engineering reflected systematic study of equipment operation under battlefield conditions. Lieutenant Colonel Yoshiro Tanaka, a communications officer with extensive combat experience in China and the Pacific, joined the analysis team in November 1943 to provide operational perspective on American communications effectiveness. His observations from monitoring American radio traffic during the Guadalcanal campaign confirmed that ordinary American soldiers operated sophisticated equipment with confidence and effectiveness that contradicted Japanese assumptions about American technical training. Tanaka's analysis of American voice procedures revealed standardized communications protocols that maximized information transfer efficiency while minimizing transmission time and operator training requirements. American forces used brevity codes, standardized formats, and systematic procedures that allowed effective coordination with minimal radio operator training. Japanese communications doctrine required extensive technical training and careful procedure adherence that limited effective radio operation to specially trained personnel. The comparison of operational doctrines revealed fundamental differences in military philosophy that extended far beyond communications equipment. American doctrine assumed that technology should adapt to soldiers, rather than requiring soldiers to adapt to technology. Equipment was designed for operation by ordinary personnel with minimal training, allowing military specialization to focus on tactical rather than technical skills. Japanese doctrine emphasized technical excellence and careful equipment operation by trained specialists. Radio operators received extensive training in equipment maintenance, circuit adjustment, and technical troubleshooting. American radio operators apparently received training only in operational procedures, relying on equipment reliability and standardized maintenance procedures that required no technical expertise. The industrial implications became increasingly clear as the analysis progressed. American military equipment was designed using commercial manufacturing principles that prioritized production efficiency, quality consistency, and cost reduction through standardization. Japanese military equipment was manufactured using traditional craftsmanship principles that emphasized individual excellence, careful assembly, and optimization of limited material resources. Dr. Yamamoto's manufacturing analysis revealed that the SCR-300 incorporated over 200 individual components, each manufactured to precision specifications that would require skilled technicians and careful quality control in Japanese production facilities. Yet the entire radio was apparently assembled by semi-skilled workers, using standardized procedures and automated testing equipment that ensured consistent quality without individual component adjustment The vacuum tube analysis provided the most shocking revelation about American manufacturing capabilities. Each tube incorporated precision electrode assemblies, carefully controlled evacuations, and specialized glass compositions that represented months of development work and weeks of skilled assembly in Japanese facilities. The American tubes showed evidence of completely automated manufacturing using precision tooling and quality control systems that eliminated individual hand assembly. Captain Hayashi examined the operational manuals that accompanied the captured equipment, discovering technical documentation that reflected American approaches to training and equipment operation. The SCR-300 manual contained detailed operational procedures, maintenance instructions, and troubleshooting guides written for soldiers with minimal technical background. Complex technical information was presented using simplified language, clear illustrations, and systematic procedures that eliminated guesswork and technical interpretation. Japanese equipment manuals assumed technical knowledge and emphasized theoretical understanding of circuit operation, component function, and maintenance procedures that required specialized training to implement effectively. American manuals assumed no technical knowledge and provided step-by-step procedures that allowed effective equipment operation and basic maintenance by ordinary soldiers. The documentation philosophy reflected broader differences in military organization and training systems. American military doctrine emphasized standardized procedures that could be learned quickly and applied consistently by large numbers of personnel. Japanese military doctrine emphasized technical expertise and individual skill development that required extensive training and careful personnel selection. The strategic implications of these differences became evident when analyzing the scale requirements for effective military communications. American forces could train radio operators in weeks using standardized equipment and simplified procedures. Japanese forces required months of training to develop effective radio operators using complex equipment and technical procedures. The time and personnel requirements for communications training had direct implications for military expansion and force deployment. American forces could rapidly expand communications capabilities by producing standardized equipment and training large numbers of operators using simplified procedures. Japanese forces were limited by the availability of technically trained personnel and complex equipment that required skilled maintenance and operation. Professor Nakamura's December 1943 report to Imperial General Headquarters included detailed analysis of American production capabilities based on component examination and manufacturing technique assessment. His conclusions painted a picture of industrial capacity that fundamentally challenged Japanese strategic planning assumptions and force projection calculations. The precision components evident in the SCR-300 required manufacturing facilities, quality control systems, and trained workforce capabilities that exceeded Japanese industrial capacity even before wartime resource limitations. The American ability to produce such equipment in quantities sufficient for standard infantry issue indicated industrial superiority that could not be overcome through Japanese innovation or resource mobilization. More disturbing still, the standardized design and commercial component integration suggested that American military production was scalable to levels that could equip unlimited numbers of military personnel with sophisticated communications equipment. The industrial capacity evident in radio production could be applied to any category of military equipment, creating systematic advantages across all aspects of military technology. The examination team's final assessment, completed in February 1944, concluded that American military communications superiority was not temporary or correctable through Japanese technical development. The industrial capacity disparities revealed by detailed equipment analysis indicated that American advantages would increase over time as production capabilities expanded and Japanese resources became increasingly limited. Dr. Yamamoto's supplemental report focused specifically on the implications for Japanese military production planning. His analysis indicated that Japan could not develop equivalent communications capabilities using available industrial resources and technical expertise. The precision manufacturing requirements exceeded Japanese production capabilities, and the scale requirements exceeded Japanese industrial capacity. The recommendation was stark. Japan should acknowledge American industrial superiority and seek negotiated settlement before the capacity disparities became so large that effective military resistance was impossible. The technical evidence indicated that continued conflict would result in systematic defeat across all categories of military equipment as American production advantages compounded over time. The warning was prescient but ignored. Japanese military leadership remained committed to decisive battle strategies that emphasized tactical excellence over industrial capacity. The technical intelligence that accurately predicted American military superiority was classified, filed, and effectively forgotten as Japanese forces prepared for campaigns that would pit traditional military virtues against systematic industrial advantages. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The reverse engineering effort revealed details that deepened Japanese understanding of American industrial superiority. The printed circuit boards, used in the SCR-300, were manufactured using photolithographic processes that Japanese industry had never successfully implemented for military applications. The precision resistors were carbon composition units manufactured to tolerances measured in fractions of a percent and tested individually for temperature stability. The electrolytic capacitors were hermetically sealed aluminum units designed for tropical service life exceeding 5 years under continuous operation. Japanese equivalent components typically failed within 6 months under similar conditions. The American components were clearly designed for equipment that would remain in service for years rather than the temporary expedient that characterized Japanese military equipment production. Dr. Yamamoto's detailed metallurgical analysis of the aluminum chassis revealed alloy compositions and heat treatment processes that provided strength-to-weight ratios superior to any Japanese military construction. The chassis was designed to protect the internal components from mechanical shock, environmental extremes, and electromagnetic interference, while remaining light enough for infantry transport. The antenna system incorporated materials and manufacturing techniques that Japanese industry could not reproduce. The telescoping elements were made from drawn aluminum tubing with precision tolerances that required specialized tooling and quality control systems. The connector systems used silver-plated contacts with corrosion-resistant platings that maintained electrical continuity under tropical conditions that would destroy Japanese equipment. Every component analysis revealed the same pattern. American industry had successfully applied mass production techniques to precision manufacturing requirements while maintaining quality control standards that exceeded Japanese laboratory capabilities. The industrial integration evident in the SCR-300 represented a fundamental advancement in military manufacturing philosophy. The strategic implications became increasingly clear as the analysis progressed. American military superiority was not based on superior individual technologies or exceptional military leadership, but on systematic application of industrial capacity to military requirements. Every piece of equipment reflected the same philosophy: design for mass production, manufacture to commercial precision standards, optimize for operation by ordinary personnel, and plan for equipment replacement rather than repair. Japanese military doctrine emphasized preservation of expensive equipment, careful operation by trained specialists, and maximum utilization of limited industrial resources. American doctrine apparently assumed unlimited industrial capacity, routine equipment replacement, and operation by minimally trained personnel. The fundamental difference in approach reflected the broader industrial capabilities of the two nations. Captain Hayashi submitted supplemental reports based on his combat experience with American communications effectiveness. His observations from the Philippines campaign confirmed that American tactical coordination depended heavily on reliable long-range communications between widely dispersed units. The SCR-300 capability explained tactical patterns that had puzzled Japanese intelligence throughout the Pacific War. American forces routinely operated with company-sized units spread across frontages that would require division-level communications for Japanese forces. Their ability to concentrate artillery fire, coordinate air support, and maneuver reserves depended on communications equipment that Japanese forces simply could not match. The communications superiority translated directly into tactical advantages that compounded American material superiority. The frequency modulation provided additional operational security that limited Japanese intelligence gathering and tactical response capabilities. American forces could coordinate operations with communications security that prevented Japanese forces from intercepting tactical intelligence and preparing appropriate countermeasures. The technical superiority created intelligence advantages that enhanced all other American military capabilities. By June 1944, the comprehensive technical analysis was complete. Professor Nakamura's final report exceeded 800 pages of detailed technical specifications, manufacturing analysis, and strategic assessment. The conclusions were definitive and devastating. Japan faced an opponent with industrial capabilities and technological integration that could not be matched with existing Japanese resources. The SCR-300 radio analysis had revealed that American military equipment superiority was systematic rather than accidental. Every component reflected industrial capabilities that Japan could not develop during wartime. The manufacturing precision, quality control systems, and mass production techniques evident in a single radio set indicated industrial capacity that could produce superior equipment across all categories of military technology. The report recommended immediate revision of Japanese military communications doctrine, accelerated development of domestic radio manufacturing capabilities, and realistic assessment of Japanese industrial limitations in extended conflict with American forces. The technical evidence indicated that Japan was fighting an industrial war with inadequate manufacturing capacity against an opponent whose industrial capabilities exceeded Japanese understanding. Professor Nakamura's personal conclusions, documented in classified memoranda that would not be declassified until 1978, were even more stark. He wrote that the examination of captured American equipment had convinced him that Japanese victory was mathematically impossible given the industrial capacity disparities revealed by technical analysis. America possessed not just superior military equipment, but superior industrial organization, superior technological integration, and superior design philosophy. The gap was not temporary or correctable through Japanese innovation, but fundamental and growing. Every month of continued conflict would widen American advantages while depleting Japanese resources that could not be replaced. His final assessment, submitted through classified channels in August 1944, concluded that Japan should seek immediate negotiated settlement before American industrial superiority rendered Japanese military resistance completely ineffective. The mathematical analysis of radio communication capabilities had revealed industrial realities that made continued resistance strategically pointless. The warning went unheeded. Japanese military leadership remained committed to decisive battle strategies that ignored industrial capacity realities. The technical intelligence that revealed American manufacturing superiority was classified, filed, and forgotten as Japanese forces prepared for final campaigns that would pit courage and determination against industrial capacity and technological superiority. Dr. Yamamoto's post-war memoirs, published in 1967 by Tokyo University Press, provided detailed insight into Japanese technical understanding of American capabilities during the final years of the Pacific War. His analysis of the SCR-300 examination revealed that Japanese engineers accurately assessed American industrial superiority but could not convince military leadership to acknowledge the implications for strategic planning. The captured radio had provided a window into American manufacturing philosophy that revealed not just superior equipment, but superior industrial organization. American industry had successfully integrated commercial mass production techniques with military precision requirements to create battlefield equipment that exceeded Japanese laboratory prototypes, while remaining simple enough for ordinary soldiers to operate effectively. The lessons learned from examining American equipment were harsh but clear. Industrial capacity properly organized and directed defeats traditional military virtues when the capacity disparity becomes sufficiently large. Superior individual courage, tactical skill, and strategic planning cannot overcome systematic disadvantages in equipment quality, quantity, and logistical support. Captain Hayashi's post-war career in the Japanese self-defense forces was built on communications doctrine that incorporated lessons learned from studying American equipment during World War II. His training programs emphasized standardized procedures, reliable equipment operation, and tactical coordination capabilities that reflected American communications philosophy rather than traditional Japanese military thinking. The communications systems developed for the Japanese self-defense forces incorporated design principles, evident in the SCR-300, mass production of standardized components, operation by minimally trained personnel, and integration with industrial supply systems that could provide equipment replacement rather than complex repair procedures. The American industrial philosophy had become the foundation for Japanese military modernization. Lieutenant Morimoto spent his post-war career with Japanese intelligence services, analyzing Soviet and Chinese military capabilities. His assessment methods, developed during the examination of captured American equipment, focused on industrial capacity analysis rather than traditional military strength measurements. He consistently argued that military capability should be measured by industrial output rather than unit strength or tactical proficiency. His intelligence assessments during the Cold War period emphasized that American military superiority over the Soviet Union reflected continued industrial advantages rather than superior strategy or tactics. The same manufacturing capabilities that produced the SCR-300 inches 1943 had evolved to produce even more sophisticated military equipment that maintained American technological superiority throughout the post-war period. The story of Japanese engineers examining captured American radio equipment parallels similar discoveries made by German and Italian technical intelligence teams throughout World War II. In every case, detailed analysis of American military equipment revealed industrial capabilities that exceeded Axis understanding and strategic planning assumptions. The SCR-300 examination provided Japanese military leadership with accurate intelligence about American industrial capacity and technological integration, but the information could not be effectively utilized within Japanese strategic planning frameworks that assumed extended conflict was viable despite industrial capacity disparities. Professor Nakamura died in 1979 at age 86. His obituary in the Journal of the Institute of Electronics and Communication Engineers noted his contributions to Japanese radio technology development, his wartime service in technical intelligence, and his post-war career, helping Japanese industry understand American manufacturing techniques. The obituary also mentioned his lifelong advocacy for Japanese industrial development that could support technological independence and military self-sufficiency. His wartime analysis of American equipment had convinced him that national security required industrial capacity that could produce precision technology in unlimited quantities rather than traditional military virtues alone. His personal papers, donated to the Japanese National Archives in 1981, included over 1,500 pages of technical reports, manufacturing analyses, and strategic assessments written between 1943 and 1945. These documents provided historians with detailed insight into Japanese technical understanding of American capabilities and the intelligence that was available to Japanese military leadership during the final years of the Pacific War. The archive also contained detailed comparative studies that Nakamura conducted between American and Japanese military equipment throughout the war. His analysis of captured American artillery radios, aircraft communication systems, and naval radar equipment revealed consistent patterns of industrial superiority that extended across all categories of military technology. Every piece of American equipment reflected the same manufacturing philosophy: precision components mass-produced to commercial standards using automated quality control systems. Nakamura's comparative analysis of the Japanese Type 94 radio and the American SCR-300 provided stark illustration of the industrial capacity disparities that determined military effectiveness. The Japanese radio required 47 precision components that were individually manufactured by skilled technicians using hand assembly techniques. Production time exceeded 80 hours per unit, and quality control required individual testing and adjustment by trained engineers. The American SCR-300 contained over 200 precision components, each manufactured to tolerances exceeding Japanese capabilities, yet production time was estimated at less than 12 hours per unit, using automated assembly and testing procedures. Quality control was achieved through standardized manufacturing processes rather than individual component testing, allowing consistent quality at production rates that Japanese industry could not approach. The material requirements comparison revealed even more fundamental disparities. The Japanese Type 94 required strategic materials, including rare metals, precision crystals, and specialized components that were increasingly unavailable as the war progressed. Component substitution and quality degradation became necessary to maintain production, resulting in equipment performance that deteriorated throughout the war. The American SCR-300 used commercially available materials and standardized components that could be manufactured using existing industrial facilities. The design incorporated alternative materials and substitute components that maintained performance specifications while using readily available resources. American equipment quality remained consistent throughout the war, while production quantities increased exponentially. Dr. Yamamoto's metallurgical analysis revealed that American equipment used aluminum alloys, steel compositions, and electronic materials that Japanese industry could not produce in sufficient quantities for military applications. The material science evident in American military equipment indicated research and development capabilities that exceeded Japanese understanding and industrial implementation capacity. The aluminum chassis of the SCR-300 used alloy compositions that provided strength-to-weight ratios superior to Japanese aircraft aluminum, while incorporating corrosion resistance that maintained structural integrity under tropical conditions that would destroy Japanese equipment within months. The metallurgy represented systematic materials research applied to military requirements using industrial production capabilities. Captain Hayashi's operational analysis documented the tactical implications of American communications superiority throughout the Pacific Campaign. His detailed study of American coordination effectiveness during the Marshall Islands campaign revealed tactical capabilities that Japanese forces could not match using available communications equipment and doctrine. American forces routinely coordinated simultaneous operations across multiple islands using portable radio equipment that maintained reliable communication over water distances exceeding 50 miles. Japanese forces lost communication contact within hours of amphibious operations, limiting coordination to pre-planned operations that could not adapt to changing battlefield conditions. The communications reliability allowed American forces to concentrate artillery fire, coordinate air support, and maneuver reserves with precision that multiplied their material advantages. Japanese forces, operating with unreliable communications over limited ranges, could not achieve tactical coordination that would offset American material superiority. Hayashi's analysis of the Saipan campaign provided detailed documentation of how American communications capabilities translated into tactical advantages that determined battle outcomes. American infantry units maintained constant communication with supporting artillery, allowing responsive fire support that neutralized Japanese defensive positions. Japanese artillery units lost communication with forward observers within hours of engagement, limiting effective fire support to pre-planned missions. The communications disparity created intelligence advantages that compounded American tactical superiority. American forces intercepted Japanese communications while maintaining secure coordination, using frequency modulation systems that Japanese monitoring equipment could not effectively decode. The information asymmetry allowed American forces to anticipate Japanese movements while concealing their own operational intentions. Lieutenant Morimoto's intelligence assessment expanded beyond technical analysis to encompass the strategic implications of systematic American technological superiority. His evaluation of captured American equipment from 1943 through 1945 revealed consistent patterns of industrial advancement that indicated systematic research and development capabilities, supporting military production. The progression from the SCR-300 radio to later American equipment showed continuous improvement in performance, reliability, and manufacturing efficiency. American industry was apparently applying systematic research and development to military equipment production, creating technological advancement rates that Japanese industry could not match using available resources and technical expertise. Morimoto's analysis of American radar equipment captured during the Philippines campaign revealed electronic sophistication that exceeded Japanese laboratory capabilities. The miniaturization, precision manufacturing, and integrated circuit design indicated research and development programs of unprecedented scale and sophistication. American military technology was advancing faster than Japanese technical intelligence could analyze and assess it. The implications for post-war military competition were clear. American industrial and technological capabilities would continue expanding after the war, creating permanent advantages that no individual nation could overcome through traditional military development programs. The systematic approach to military technology development evident during the war would continue, maintaining American superiority across all categories of military equipment. Professor Nakamura's strategic assessment, completed in March 1945 as American forces approached Japan, provided comprehensive analysis of the industrial warfare lessons revealed by 3 years of captured equipment examination. His conclusions challenged fundamental assumptions about military power, technological development, and strategic planning that had guided Japanese military thinking for decades. Modern warfare, Nakamura concluded, was determined by industrial capacity rather than military tradition. Victory belonged to the nation with superior manufacturing capabilities, technological integration, and systematic application of commercial production techniques to military requirements. Traditional military virtues remained important but were insufficient when facing opponents with systematic industrial advantages. The American approach to military technology represented a fundamental revolution in warfare that Japanese military doctrine had failed to recognize and adapt to. American success was based on industrial organization rather than individual excellence, systematic standardization rather than craftsmanship perfection, and mass production rather than specialized manufacturing. Japanese military culture emphasized individual skill, technical excellence, and careful resource utilization. These virtues were admirable but insufficient when competing against systematic industrial capacity applied to military requirements. The examination of American equipment had revealed that modern warfare required industrial capabilities that Japan simply did not possess. Nakamura's final recommendation was uncompromising. Japan should acknowledge American industrial superiority and seek immediate negotiated settlement before the capacity disparities became so overwhelming that meaningful resistance was impossible. The technical evidence indicated that continued conflict would result in systematic military defeat across all categories of equipment and capability. The recommendation was politically impossible and strategically ignored. Japanese military leadership remained committed to decisive battle concepts that emphasized tactical excellence over industrial capacity. The accurate technical intelligence that predicted American military superiority could not overcome strategic thinking that refused to acknowledge industrial warfare realities. The post-war occupation period provided Japanese engineers with unprecedented access to American military technology and manufacturing systems. Dr. Yamamoto served as technical advisor to occupation forces, helping translate captured German and Japanese technical documents while learning American manufacturing techniques that would transform Japanese post-war industrial development. His exposure to American quality control systems, automated manufacturing processes, and integrated production planning provided insight into the industrial organization that had produced the SCR-300 and thousands of other precision military equipment items. The manufacturing philosophy that impressed Japanese engineers during wartime examination became the foundation for Japanese post-war industrial modernization. The statistical process control, standardized procedures, and systematic quality management that characterized American military production were applied to Japanese civilian manufacturing during the 1950s and 60s. The industrial techniques that produced superior American military equipment became the basis for Japanese automotive, electronics, and precision manufacturing industries. Captain Hayashi's post-war career with the Japanese Self-Defense Forces incorporated communications doctrine and training procedures based on American military practices observed during the war. His training programs emphasized standardized procedures, reliable equipment operation, and tactical coordination capabilities that reflected American military organization rather than traditional Japanese approaches. The communications equipment developed for the Japanese self-defense forces incorporated design principles and manufacturing techniques learned from studying American equipment during the war. Standardized components, automated quality control, and systematic maintenance procedures replaced traditional Japanese emphasis on individual technical expertise and careful equipment preservation. Lieutenant Morimoto's intelligence career during the Cold War period applied analytical techniques developed while examining American equipment during World War II. His assessment methods focused on industrial capacity analysis, technological integration evaluation, and systematic capability measurement rather than traditional military strength indicators. His intelligence assessments consistently emphasized that military capability should be measured by industrial output rather than tactical proficiency or unit strength. The lessons learned from analyzing the SCR-300 radio provided analytical framework that remained applicable to evaluating Soviet and Chinese military capabilities throughout the Cold War period. Perhaps the most significant document in the collection was a personal letter Nakamura wrote to his son in September 1944 as American forces approached the Philippines. He reflected on the 18 months spent examining captured American equipment and the conclusions that analysis had forced him to accept. America, he wrote, had successfully industrialized warfare to a degree that traditional military planning could not address. They had applied the same mass production philosophy that built consumer goods to military equipment production, creating industrial capacity that could overwhelm any opponent through sheer volume of superior equipment rather than tactical brilliance or individual courage. Japan, Nakamura observed, had attempted to fight an industrial war using traditional military methods. The examination of American radio equipment had revealed that this approach was fundamentally flawed when facing an opponent with systematic industrial advantages. Victory in modern warfare required industrial capacity that could produce precision technology in unlimited quantities, something Japan could not achieve with existing resources. He concluded the letter with observations that proved remarkably prescient. The next major conflict, he predicted, would be even more dependent on industrial capacity and technological sophistication. Victory would belong to the nation with the greatest manufacturing capability, the most advanced technology, and the ability to produce precision components faster than any opponent could destroy them. America had demonstrated these capabilities during World War II through equipment like the SCR-300 radio. Any future opponent would need to match or exceed American industrial output, something Nakamura believed was impossible for any single nation. The industrial advantages that enabled 20-mile radio communications in 1943 would expand to encompass satellites, computers, and precision-guided weapons. History validated his assessment. The Cold War became a competition of industrial capacity, technological innovation, and manufacturing efficiency. The Soviet Union, despite continental resources and massive population, could not match American electronics production, computer technology, or precision manufacturing. The gap that Nakamura identified in radio components in 1943 expanded to encompass every category of high-technology military equipment. The story of Japanese engineers examining captured American radio equipment is ultimately a story about the transformation of warfare from an activity determined primarily by military skill to one determined by industrial capacity. The SCR-300 radio represented the moment when battlefield communications became an industrial product rather than a military specialty. The 20-mile communication range that so impressed Japanese engineers was not achieved through superior military communications doctrine, but through superior industrial organization applied to military requirements. American industry had learned to produce precision electronic components to military specifications using mass production techniques that had never been attempted at that scale. This capability, developed for military radio equipment, extended to every aspect of American military production and eventually to every category of consumer electronics manufactured in America. The lessons learned by Japanese engineers examining American equipment in Tokyo were lessons about industrial warfare and the revolution in manufacturing that occurred in America during World War II. The frequency crystals, vacuum tubes, and circuit boards that revealed American industrial superiority became the foundation for the electronics industry that dominated global technology development for the remainder of the 20th century. The manufacturing philosophy, evident in the SCR-300 radio, established principles that govern modern electronics production: design for manufacturability, standardize for interchangeability, automate for precision, and scale for demand. The direct line runs from radio components analyzed in Tokyo in 1943 to microprocessors produced in Asian foundries in the 21st century. The industrial philosophy remains unchanged. Only the scale and sophistication have increased. The Japanese engineers who examined captured American radio equipment were witnessing the birth of the modern electronics industry. Their detailed reports, classified and filed during the war, eventually became historical documents that explained not just why Japan lost the Pacific War, but how industrial capacity determines the outcome of modern conflicts. Their conclusions, written in technical language but unmistakable in meaning, identified principles that remain relevant in an age of satellite communications, computer networks, and precision-guided weapons. Industrial warfare demands industrial capacity. Superior individual equipment means nothing if it cannot be produced in quantity. Sophisticated technology is useless if operators cannot reliably employ it. Theoretical excellence is worthless if manufacturing cannot achieve it consistently. These lessons, learned by Japanese engineers examining a single American radio in 1943, became the foundation for understanding modern military competition. The SCR-300 radio, with its 20-mile range and foolproof operation, represented more than superior communications equipment. It represented the industrialization of military technology and the transformation of warfare from a contest of military skill to a competition of manufacturing capacity. The nation with greater industrial ability to produce high-technology equipment in overwhelming quantities would ultimately prevail. America proved this principle during World War II. Japan learned it through detailed technical analysis of captured equipment. The world has been adapting to its implications ever since. In an age of precision-guided weapons, satellite surveillance, and computer-controlled warfare, the fundamental truth identified by Japanese engineers in 1943 remains unchanged. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.